You're testing a modern React or Next.js application. You click from the user list to the analytics tab to the billing page. The UI feels snappy, throwing up skeleton loaders as you bounce between heavy views. But if you open the network panel, a different reality unfolds. Every click spawns a new batch of requests. Instead of clearing out, they stack up, forming a cascading, infinitely growing waterfall of pending network calls. The code running this interface looks perfectly fine. There are no infinite loops, there are no syntax errors. Every component mounts and unmounts exactly as the framework dictates. Yet while your front end appears clean, your backend is under siege. Your database is spending CPU cycles computing complex queries for views you abandoned seconds ago. Browsers typically cap concurrent connections to a single origin at about 6 over HTTP 1.1. These orphaned requests hog those limited slots, blocking the data you actually want from loading. Destroying the UI component doesn't terminate the work it asked for. By leaving those tasks running, this application is building up a silent, systemic memory and infrastructure leak. It's a common developer misconception that when a component unmounts, its background tasks die with it. Modern operations like fetch operate independently of your component lifecycle. Once invoked, the actual network request is offloaded away from the main thread. This creates the ghost request. The user has moved on, the UI is gone, but the network call is still out there, consuming bandwidth. The danger lies in how JavaScript manages memory. The pending promise waiting for that request maintains a closure over your application's variables. Because those variables are still referenced by the promise, the garbage collector cannot reclaim that memory. A promise in JavaScript is rigidly defined. It sits in a pending state until it definitively fulfills or rejects. Until one of those two things happens, its memory footprint remains walked. If you fetch data asynchronously without an explicit cancellation strategy, you are guaranteeing a memory leak at scale. JavaScript executes on a single primary thread. To handle asynchronous work without freezing the page, the runtime delegates operations to the browser's background threads. When calling fetch, it starts on the call stack but is instantly handed to the web APIs. The user clicks a new tab. The call stack clears completely, but the fetch continues running in the background, holding a reference to the main memory heap. The .then or await continuation attached to that fetch is waiting to update a piece of UI state. Even if that UI no longer exists, the anticipation of that callback acts as a physical barrier to the garbage collector. Because the event loop separates execution from networking by design, the system will never clean this up automatically. You have to manually sever the tether. This architectural flaw also surfaces as active state corruption. Take a standard autocomplete search input. As you type, every single keystroke fires a new, parallel network request. Suppose you type the letter A. The server takes 500 milliseconds to process it. A moment later, you finish typing APP. That request is highly cached and returns in just 100 milliseconds. We now have a timeline inversion. The fast request for APP resolves first, and the UI displays the correct data. But that delayed request for A is still running. When it finally resolves, its orphaned promise executes the state update, overwriting your correct data with stale results. The network layer makes zero guarantees about the order in which parallel responses will arrive. State corruption is the direct outcome of allowing parallel network requests to overwrite each other. Here is how developers write a component fetch. They call the endpoint, parse the JSON, and update the state. There's no mechanism to stop it. The native solution to this is the AbortController API. It serves as a direct mechanical bridge between your UI and the browser's network layer. You instantiate the controller, extract its signal property, and pass that signal directly into your fetch configuration options. To use it, you invoke the abort method on the controller during the component's cleanup phase, or right before initiating a new request on the next keystroke. When you call abort, the browser takes immediate action. It forces a TCP reset, instantly halts the background web API thread, and throws an exception to stop the JavaScript execution. Calling abort is the physical act of severing the closure tether. The background task dies, the memory references are dropped, and the garbage collector immediately sweeps the orphan data. When we return to the rapid clicking dashboard and apply this controller, the network panel reflects the user's intent. The exact moment you navigate away from a complex view, all of its pending requests are instantly halted. Your client memory heap remains perfectly flat, and the backend database processes 0 abandoned queries. One vital detail: an aborted fetch throws an abort error exception. If unhandled, it can crash your application or pollute your telemetry logs with false positives. Inside your try-catch blocks, explicitly check if the error name matches abort error. If it does, you safely swallow the rejection and do nothing. Proper error handling transforms a violently canceled network request from a noisy exception into a clean, successful cleanup operation. Passing an abort signal establishes a foundational safety mechanism. It synchronizes the single-threaded UI with the physical limits of the network. Failing to cancel an obsolete fetch introduces state corruption and a persistent memory leak.